Today, I will present the topic change of variables in multiple integrals. Why change variables? While often the reason for changing variables is to get us an integral that we can do with the new variables, another reason for changing variables is to convert the region into a nicer region for us to work with. When we're converting the polar, cylindrical, or spherical coordinates, we didn't have to worry about this change since it was easy enough to determine the new limits based on their given region. Single variable integral. In one-dimensional calculus, we often use a change of variable, namely substitution, to simplify an integral. We can write the substitution rule as the integral of a to b fx dx equaling the integral of c to d f gu g to the derivative u du, where x equals gu, a equals gc, and b equals gd. Double variable integral. The change of the variables can also be useful in double integrals. In order to change variables in a double integral, we will need the Jacobian of the transformation given by x equals guv, y equaling huv. The Jacobian is defined as a determinant of a 2 by 2 matrix as shown on the slide. Now that we have the Jacobian out of the way, we can give the formula for change of variables for a double integral. Change of variables in a double integral. Suppose that we want to integrate fxy over the region R. Under the transformation x equals guv, y equals huv, the region becomes S, and the integral double integral r fxy dx dy becomes the integral as shown on the slide. We change an integral in x and y to an integral in u and v by expressing x and y in terms of u and v. Example 1. Calculate a circle area. Let's do an integral to calculate the area of a circle to transform the xy plane to r theta plane. The new variables of r and theta are related to the old variables x and y by the equations x equals r times cosine theta and y equals r times sine theta. The Jacobian of this transformation is shown on the slide, which equals r. Example 1 continued. Continue the calculation, which gives us a equals the integral of 0 to 2 pi, the integral of 0 to r dr d theta equaling pi r squared. This explains why there's an r factor in polar integrals. The area element dA equals dx dy is not equal to dr d theta. Instead, dA equals r dr d theta. Triple variable integral. There is a similar change of variables formula for triple integrals. This transformation maps the region R in the xyz space to the region S in the uvw space. To do the integral, we will need a Jacobian, just as we did with double integrals. The definition of the Jacobian for this kind of transformation is the following 3 by 3 determinant as shown on the slide. We use the following formula for triple integrals, triple integral R f xyz dx dy dz as shown on the slide. Example 2. Calculate a volume. In this example, we need to calculate the volume inside the surface. X over a to the power 2/3 plus y over b to the power 2/3 plus z over c to the power of 2/3 equals 1. Let x equal a times u to the cubed, y equals b times v to the cube, z equals c times w to the cube. Then, in the uvw coordinates, the surface becomes u squared plus v squared plus w squared equals 1. The Jacobian of this transformation is shown in the slide, which equals 27 abc u squared v squared w squared. Example 2 continued. Continue the calculation of the triple integral r dx dy dz equaling the triple integral of r 27 abc u squared v squared w squared du dv dw. Now the transformation uvw to spherical coordinates r, theta, and phi. Du dv dw will become r squared sine phi dr d phi d theta. The triple integral as 27 abc u squared v squared w squared du dv dw is shown in the slide. The final volume equals 4 pi over 35 times abc. Thank you for watching. I hope you've had a great day.